Saxon Advanced Mathematics, Lesson 73. Hi ladies, our topic today is regular polygons. But that's a little bit misleading. That doesn't reveal to you the pure magic of what we're gonna do. It's a quick lesson. There's only 2 examples. And what we're working with is the idea that within a circle, we can inscribe a regular polygon, a triangle, a square, a pentagon, a hex. Notice that when we do this, the shape that we put into the circle is perfectly even. Notice that parts of the polygon are equal to the radius of the circle, right? That's interesting. The vertices of the polygon actually touch the circle in all the cases. The center of the polygon is also the center of the circle. And we're going to use a variety of tricks that we know. Oh, the other thing I wanted to tell you is that if we divide the polygon up into triangles, each of these can be written as an isosceles triangle. Right, these are isosceles triangles, and they can be, we can calculate an altitude, or what we call apothem of each triangle. The altitude of the triangle is called the apothem of the polygon. Okay, we'll look at that in just a minute in more detail. Fancy names. And also, if you take the polygon and put a circle inside the polygon, no. Yes. No, never mind. I don't want to say anything about that. So the radius of the circle has a place in the polygon, although it's different depending on the polygon. Okay, so what we're going to do is we're going to answer questions about the polygons using a variety of tools, including our trig functions. All right, let's dive into it and you'll see what I mean. Find the area and perimeter of a regular pentagon, 5 sides, thank you, John, he tells us, that is inscribed in a circle whose radius is 6 units. Okay, so we draw. John does not provide a picture in the problem. He does in the solution, but we'll draw that. Just notice that because we're talking about a pentagon, we're drawing this shape roughly, right? We're gonna go to the middle and we're gonna draw 5 radii that come out, and those are going to be the, they're gonna lead us to the vertices of our polygon, all right? So it won't be perfect, but that's okay. Let's figure out the centers right about here, and then we'll go. It's sort of like a starfish is how I always think of a pentagon. Kind of like this, right? And then if we wanna clearly see the pentagon, we can connect the dots. Okay, we want to find, we want to find the area and perimeter of the pentagon, not the circle, the pentagon. Okay, what I like to do is I like to draw the triangle bigger, so I can really get my labels in. So this triangle is going here. All right. The circle whose radius is 6 units. So what that tells us, the radius is this side and this side. So it's this side and this side. That tells us that those are 6. We also know that we can drop a perpendicular down right there and turn this into 2 turn it into 2 right triangles. Sorry, my brain fell asleep there. Now, first of all, let's figure out that's what we know already. Now let's figure out what we need to know. Let's start with the perimeter. We're gonna need these sides, right? All the way around to get the perimeter. But that's just this measure times 5, right? Let's call it x. Okay, the perimeter equals 5 times that side. Okay, so how can we find this side? We know this is 6. We know that's 90 degrees. Is there any way we can find out information about an angle? Not those angles, but we can easily find this total angle because 1, 2, 3, 4, 5 of those has to equal 360. So if we take 360 and divide it by the 5 angles that make the pentagon, I'm just dividing 360 by 5. We'll find out that this is 72 degrees. And if we want just half of that so that we have a right triangle so that we can use trig equations, we can call this 36 degrees. So now we're looking at just the half of this triangle, the right triangle piece of it. All right, we want to know this, which is the opposite, right? So we know that the sine of 36 degrees will equal the opposite over the hypotenuse. It will be, I'm going to call it, let's call this whole thing 2x, and we'll call this side just x. Does that make sense? Because I want to talk about just half of it right now. I don't want to talk about the whole length. So x is the opposite, and 6 is the hypotenuse. Aha! So what that tells us is that if we solve this, 36 degrees at the sine function times 6, that equals 3.53 units, 3.527 rounded, right? Now, oh wait. Yes. Okay. Now, we need to take this unit, this measurement, and figure out how many of those we need to go around the whole circle. We figured out that this long thing, which we're now calling 2x, we need to do 5 times. And I didn't change this, right? If one of these is called 2x, we need 5 of those going around. Or another way of looking at that is that since we measured half of that base, because we turned it into a right triangle, we can do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times around, right? So 3.53 is this length times 10 because there's 10 segments like that in the perimeter, means that the perimeter of the polygon is 35.3, what's our unit? It doesn't tell us, so we just say units long, and that is the correct answer. Kind of fun, right? Kind of easy, not too bad. Okay, now we want to find the area. To find the area of this triangle, of which we have 5 of them, right? We need to find the base times the height, right? Area equals base times the height divided by 2, and then we'll have to multiply it by 5 because there are 5 triangles in this. Okay, we know the base of the whole thing. The base equals, we'll double this, right? And that would be 7.06 the height, right, because I doubled this. I doubled that. 3.53 is the length of x. So the full height, the full base would be 7.06. The height, we don't know yet. We don't know this measure, but we could figure it out, couldn't we? Because if we use cosine of 36 and this as the hypotenuse, then we can get this. So let's say 6 hypotenuse times the cosine of 36 degrees will equal the height. Okay, 6 times the cosine of 36 degrees is 4.85. So the area of this whole triangle is I'm going to number these. Okay, so the area of this whole triangle 1 is that times that divided by 2. I'm just double checking my logic to make sure that's right. Okay, and then to get 5 of those, we can multiply the whole thing by 5 over 1, right? So this is dividing by 2 because that's the formula for the circle, and it's multiplying by 5 because we have 5 triangles. Okay, so I went from finding just the area of the first triangle and then multiplying that number by 5 to get the final answer. And that should be, let's see, this is roughly going to be 35, 17. Okay, it should be about 85.6 units squared. And John did his numbers in a slightly different order than mine. So I'm going to multiply a little bit on the side here and see if I can get the same as him. Sorry, I'm just flipping through my little baby book here. Okay, 7.06 times 4.85. So I'm going to multiply this much first. Okay, 1, 2, 3, 4. That is this much. Then I'm going to multiply it by 2.5 because that's 5 over 2 simplified. I'm not coming up with the same number as John. It could be just craziness in my multiplication. I'll check that and get back to you. But in any case, you can see what we're doing here. We are using sine and cosine to find missing values that are required to find the area and perimeter of the pentagon. In this example, I'll follow along with John's calculations a little more step by step so that I get the right answer. And I'll get back to you on that. I'll check that and text you. The perimeter of a regular polygon of 8 sides is 48. Okay, so the perimeter is 48 units. Find the area of the polygon. Okay, so we have a circle. There are 8 sides. Now, I don't want to try and draw an 8-sided polygon. So what I'm going to do is I'm just going to draw one triangle. All right? And I'm going to figure out how many degrees are at the top of it. It will be 360 divided by 8. Let's see, that's 4. 8 times 4 is 32. I subtract, I get 40. Aha! 45 degrees up here, right? So that means if I draw just the isosceles part of this triangle, this will be a 22.5 degree angle, right? Okay, I like that. The perimeter is 48 and it's got 8 sides. That tells me that there are 6 units on each side. This is 6, this full length, right? And that means that this is 3 units, right? So I take the 6 and I divide it in half for just one little bitty bit, right? Now, I'm trying to find the area. The area is going to be the base times the height of my triangle. Okay, so I need this. I'm going to call that A for the altitude this time, rather than H for the height. Same difference, right? And we know that we don't have the hypotenuse this time, so we're going to have to work off of tangent. Tangent is opposite over adjacent. So we know that the tangent of 22.5 degrees is going to be equal to the opposite over the adjacent, and that's the mystery letter. So to solve this, I'm going to have to cross multiply and rewrite this as A equals 3 over the tangent of 222.5, not 200.5 degrees. And if you enter that into your calculator, you'll get an altitude of 7.24. That's this measurement. Whoops. So now, what we want to do is, John likes to do it, he likes to run the calculation on the small triangle. That's where I went different from him last time, is that because now we know the base and the height of the full triangle, I don't see any need to limit our calculation to this half triangle. But John likes to keep it at the half triangle. So he says the area of the half triangle equals the base times the height divided by 2. Yes. And that is, the base is 3. The height is 7.24. And then we divide it by 2. And that equals 10.86 square units. So that's the area of this much, half of one of those. Now, how many do we multiply it by for the whole circle? Well, there are 8 full triangles, so there are 16 half triangles. So 16 times 10.86 equals 173.76. And that units squared. And that is the area of the full polygon with all 8 triangles, even though we just drew one, because we don't need to sit here all day drawing triangles that we really don't need. We just need one of them. And one of the 8 helps us get our bearing for half of the 8 because it's the half triangle that is a right triangle that allows us to use sine and cosine fluidly. We know that we could use the law of sines with this, but we don't want to do that. We want to get right to this triangle. All right. And I want to go back now that I see so clearly what John is doing different than me. Let's go back to this triangle and say, okay, 7 point, let's go back to our half triangle. We want to find the area of the half triangle. So that's the base of the half triangle times the height divided by 2. The base of the half triangle is 3.53, right? That's what we got right there. So it's 3.53 times the height, which we calculate as 4.85. And then we divide that by 2. Again, that's the area of the half triangle. Okay, and that equals 8.56 square units. I'm just repeating myself here so you're super clear on what we've calculated. I'll just put a unit on that so you're sure. And in this one, we were dealing with a pentagon. And so we have 10 half circles. So our final calculation is 85.60 units squared, right? Because we took the area of one of the half triangles and we multiplied it by 10. We have a total of 5 triangles and they each have 2 pieces. That's where the 10 came from. We multiplied it by that same area and we get this, okay? That should work out to be the same as what I had, but my numbers were not quickly getting me there, so I'll double check that still just to make sure I wasn't making a mistake. But this way we work the problems with John's approach. And again, what John is doing is once he breaks the triangle down to this half size, in order to use sine to get this side and cosine to get this side, then he doesn't expand it back to be the full triangle. He just leaves his measurements in this size and then multiplies up not by 5, but by 10, looking at each of these as a half triangle. So we need 10 instead of 5. I hope that makes sense. I hope I didn't blow your brains. Okay, that's all for lesson 73. Kind of cute, kind of fun, right? Goodbye.